Hello, welcome to NPTEL online certification course on Introduction to Application of AI to Robotics. Today we are going to continue from my previous lecture on machine learning where we studied the supervised learning. So today I am going to take an example of the supervised learning where we will be looking at how can a robot be learned basically to pick up an object, and then explain the critical concept of generalization, overfitting and underfitting, and understand unsupervised and reinforcement learning. The contents are organized in this way. Then finally, I will introduce a topic on the reinforcement learning. We have a dedicated lecture on the reinforcement learning. So, only few slides I will be using just to brief you what the reinforcement learning is. Okay. So, let us take an example. So, last class we have learned about the supervised learning, right. So, suppose I have a problem, that is the lifting torque calculation for a robot arm. So, let us see that this is my robot arm which is available in our lab, and suppose this arm has to pick a weight, right. And let me give you an example. Suppose I say that this angle is say 0 degree, this position, okay, so that this arm stretches basically, okay. So, this is the configuration, say, alright. So, here my problem statement is that how much torque is required by robot arm, that is say this joint motor, okay, to lift the box, alright, based on the weight of the box and how far the arm is extended, alright. So, suppose this is the problem statement, right. Okay. So, the data architecture could be input features, could be in the form of weight and how much is the extended distance. Okay. For the maximum stretch, we can take this configuration and we are trying to calculate the joint torque here. So, basically what I am saying is that we are able to change the two parameters, one is the weight and other is the extended distance, okay, and say the output is the torque, okay, which is a floating point number. So, the linear regression which we have seen in the previous lecture, okay, we are going to use this algorithm to find out what could be the torque requirement, although this example is very primitive in nature, alright. But I just wanted to illustrate that how can we use the concept of linear regression, okay, to find out the torque requirement for the unknown load and the extended distance, okay. So, to begin with, what we do here is that first we import NumPy and matplotlib, okay, and then we import the linear model. You see NumPy is a core math library. Matplotlib is for the data visualization, we have been seeing this, okay, and linear regression model from the skit-learn, alright. So, here I have this synthetic data which we have generated, okay. So, for 1 kg weight and extended half a meter, say this one. Then we have say 2 kg weight extended half a meter, again 1 kg weight extended by 1 meter and 5 kg weight extended by 1 meter. So, these are the synthetic data which we have generated, and then the torque requirement could be something like this. Again, this is synthetic data which we have just got by multiplying mass with g, okay, and with your extended this arm length, alright. So, this 1 into 0.5 and into 9.81, right. So, if you multiply this, we will be getting a torque value. So, let us say that torque value is 4.9, okay, for this one. Then for the second case, you have the 9.8, for the third case again you have 9.8, and say for the fourth case it is say 49, okay, since they are synthetic data may not be very precise one, okay. So, here you see this is our feature matrix X, okay, and it contains 4 past experiences. So, my input data is 4 cross 2, that is 4 rows, 1, 2, 3, 4 and the 2 columns, first column and the second column, right. Okay. So, that is the output torque of 4 past experiences, alright. So, here we select the linear regression, right, and the algorithm goal here is if you have one feature then naturally a straight line, but for the 2 features we need to draw a plane basically, and for the higher dimensions we need to draw a hyperplane, okay. So, feed data into the model. So, this data and this data, okay, is being fed into, okay. And then we say that suppose I have got a new box, alright, with say weight of 3.5 kg and say the stress length of 0.8 meter, and this one dot predict take new data point to the model and tell us the torque output basically, alright. So, this is my object weight and this is the arm extension, okay, and we have the motor torque requirement, okay. So, these two are the input data and the motor torque is the output data basically. So, when we plan our 4 cases 1, 2, 3, 4, so this is the plane which we are going to get basically. So, these are my training data, okay, and so this is my new test point. So, for that new test point how much torque will be required, we can get a point in this plane and then we can extend that actually, okay, such that intersect this plane basically, and then we will be getting that torque output, okay. So, this way we get the regression result, okay. So, it predicts say 31.04 Newton meter of the torque required. So, this way we can use the supervised learning for predicting the unknown, right, okay. So, any supervised learning, the ultimate goal is to build a model basically, right, that can perform well on the new or never before seen data as we have seen previously, okay. Our model was not trained on the test data, right. So, there is a concept called generalization, and it says that a model is generalized if it can take mapping learned from the training set and apply them accurately to a test set or the real world data with similar characteristic, right. And you see, the model can always memorize a training set perfectly. The only true measure of generalization is its performance when we are giving the test set, right. So, we want to build a model that is able to generalize as accurately as possible. Next, there is a concept of overfitting and underfitting, okay, in the supervised learning. What is overfitting actually? Okay. So, see, we always try to model, right, based on the data, okay. So, you see that when our model is very much complex related to the amount of the information or the training data available. Now, when this model fit very closely to the particularities of the training set, then what happens? It will work very well with the training data, okay, but it may not work very well with the your test data, right. So, it will not be able to generalize to the new data, okay. So, what are the symptoms for that? The symptoms are that you are going to have low training error, but very high test error, okay. So, this is what happens when your model is too complex, okay, and this is what we call as the overfitting, alright. So, what is cause for this? Okay, you see the too many features related to the number of samples which you are taking, okay, too many training iterations, okay, using highly flexible models. These are the causes, okay. And next, what if your model is too simple, okay, to capture the essential variability and the pattern in the data, then what is going to happen? In that case, you are going to have very high training error as well as your test error are also going to be high, okay. And the causes for this, naturally the insufficient features, strong regularization, okay, that basically stifles the model ability to learn, okay. So, that causes what we call as the underfitting, okay. If your model is too simple and if your model is too complex, it is the overfitting. Okay. So, what need to be done actually? We need to have a trade off. So, as I said, if you look at the model complexity, you see if your model is underfit, then your accuracy is going to be low with the training as well as with the generalization. But if your model is overfitted, then your training accuracy is going to be very high, but with the generalization accuracy is going to be low, okay. So, what is to be done? So, we need to find out some sweet spot where we can have an optimal model, okay. So, every design decision have how many number of features we are going to take, regularization strength, data set size, and what are going to be our evaluation strategy. Okay. So, as I said, ultimately we are going to come down to the trade off between underfitting and overfitting. Okay. And this is what we have seen already. Generalization, the training error is low, test error is also low, and this is the desired model which we want to have. In case of overfitting, your training error is going to be very low, but test error is going to high, and the reason is the model being too complex. And for the underfitting, your training error is also going to be high and test error is also going to be high, and the cause is that your model is too simple. Okay. Next, let us move on to another very important topic in machine learning, that is the unsupervised learning. Okay. So, you see, in case of supervised learning, we have data in form of the input and output, both were available, right. But in case of unsupervised learning, we have only input, we do not have the output. Okay. So, it is a machine learning algorithm that shows only input data and is expected to extract the knowledge or regularities on its own from the input model. Okay. So, as I said, in this case we do not have the labeled output, okay, or the teacher provide guidance to the algorithm for the knowledge extraction. Okay. So, the goal of the algorithm is to extract knowledge from the data. So, how it could be done? It could be done by identifying the patterns in the data and regularities, okay, and underlying structures. Now, you see, to no labeled data available, there are some primary challenges. Okay. What are these challenges? The major challenge is to evaluate whether the algorithm learned something useful or not. Why I am saying useful or not? Because we do not have anything to compare, right? We do not have information on the correct output, okay, and the result often require manual inspection or exploratory analysis because we do not have any output data for the given input. Okay. So, there are two major types of unsupervised learning, okay, and these are the unsupervised transformations and the clustering algorithm. Okay. So, let us see the first one, unsupervised transformation first. Here basically what we do is that the algorithm create a new representation of the data. So, whatever data is there, a new representation is created out of that, okay, and with that new representation it is easier for the user, okay, to understand, okay, other ML algorithm to understand. What are the key applications? Key applications are, say, dimensionality reduction or the feature extraction. Okay, if from a given data we want to extract some feature, okay, so that is the application. And some of the popular algorithms, principal component analysis, non-negative matrix factorization. Next type of the unsupervised learning is the clustering algorithm. Here you see that algorithm that partition data into distinct groups, basically distinct groups of similar items. Alright. So, the clustering algorithm segregate that groups basically, okay, where point within a single cluster are very similar and point in different clusters are distinct. Okay. There are two popular algorithms, the k-means and the density based spatial clustering. Okay. Here in today's lecture I am going to elaborate much more on the k-means algorithm. Okay. So, let us see the clustering k-means algorithm. Okay. What does this means basically? Okay. So, you see this k-mean algorithm basically is one of the most popular and straightforward unsupervised learning algorithm which partition a data set into k distinct non-overlapping group, okay, and these groups what we call as the clusters. Okay. So, how does the algorithm work? Basically you have the input data here in this form, store the data, then we are going to declare the k points randomly. Okay. So, here we have k is equal to 3. So, I am declaring a cluster 0, say this one, then cluster 1, say this one, and the cluster 2, this one. This has been done randomly, right. And after doing this, the next step is to assign each data point, okay, to the closest cluster center. Alright. So, here we assign these data to the cluster 0, okay, and here this data closer to cluster 1, and you see that this one they are also assigned to same cluster, and this is cluster number 2, alright. Okay. Then next step is what we do. Now we update the cluster center, okay. So as the mean of the cluster data, okay. So you see we began with arbitrarily assigning those k points randomly, right. But now here we are updating that by finding out the mean of the cluster center, okay. And then after we have identified that, then again we go assign each data point to the closest cluster center, okay. So that reassignment we do, okay. So and after that again we update the cluster center, okay, as the mean of the clustered data. So this process we keep on doing here, alright. So you see if cluster center remains unchanged, then we stop basically, okay. And so in this assignment process you see that the cluster center, this red one which was earlier here, that has moved to here, alright. So this is how we execute the k-mean algorithm, okay. And when our cluster center doesn't change, algorithm stop and returns your k clusters. Okay, so let us try to understand this with the help of an example, okay. Say my problem statement is that I have got an autonomous robot, okay, which is navigating in an unknown indoor environment and continuously recording sensor data, okay. Say the sensor data temperature and the Wi-Fi signal strength, alright. So the data architecture is your temperature and the Wi-Fi signal strength. We do not have any labeled output data, alright. So let us apply the k-mean algorithm which we have studied previously, okay. So the motivation here is based on the sensor reading, divide the area into say 3 distinct zones, okay, based on the temperature and the Wi-Fi signal strength, okay. So here we begin with importing NumPy and matplotlib, okay, and this NumPy we have seen it is a core math library, and matplotlib is for the data visualization, and k-mean model, okay. So here is the data, alright. So you have the term say temperature here and the Wi-Fi signal strength here, alright. Then here we have the standard deviation, that is temperature could vary say plus minus 2 degrees and Wi-Fi strength could vary say plus minus 5%, okay. And from this information we generate output matrix is say 100 cross 2, okay. So generate 100 rows, okay, of data, and the 2 columns basically one corresponding to temperature and one corresponding to the Wi-Fi strength, okay. So likewise these 3 sets of data are available. So one is say cold and bad Wi-Fi, and then the other one say warm and great Wi-Fi, and say other one is warm and okay Wi-Fi, okay. So this is the data which is available. Okay, so here it stacks all sensor data into 300 rows cross 2 column matrix, okay, and you see that we do not have any output array, right. So we do not have any y value. So here we select the k-mean model, okay, the k-mean model with the number of clusters I say that 3, right, and we use dot fit, okay, it feed only x data into the model here, x insert data, and my new reading is 23-degree temperature and 85% Wi-Fi strength. You see for the model testing we provide new data point to the model, dot predict, it will take new data point to the model and find the closest cluster, okay. So here is the plot, so you have the temperature and Wi-Fi strength, okay. So we have generated those 100 data points for the each zone, right. So we have these 3 zones, alright. We classify say this is zone 0, this is zone 1 and this is zone 2, right. The 3 clusters basically, and the zone centers are also marked here, alright. And say this is my new reading coming over here, and so with the location of the new reading I can predict that it belongs to zone 0, okay. So the new reading has been 23 degrees centigrade and 85% Wi-Fi strength, Okay, so as you can see that this is around 23 degrees centigrade and something around 85% Wi-Fi strength. Okay, so robot classifies I belong to zone 0. So you see, in unsupervised learning, there could be the various robotics examples. These are, say, clustering I have just explained. Okay, so the robotic application could be terrain type from raw LiDAR data. We have LiDAR data, okay, and from that LiDAR data we can describe what terrain type is. Then we can have anomaly detection, okay, that is identifying abnormal in joint torque patterns due to, say, mechanical failure. Okay, so if we have a data where we have the joint torque information is there, okay, and if some joint torque value is peaking at some point of time, then probably we can say that no, some mechanical failure has come. So that way we can detect the anomaly. Okay, then we can use it for the dimensionality reduction. Okay, that is, we can compress the LiDAR scan data to a compact representation, okay, for the real time processing. And we could also think about the compression of the images. Okay, so grouping similar pixel color to represent an image using fewer bits. Okay, so that is what we can do in the image compression. Okay, now let us see the last part of it. I have just kept here to introduce you a little, because as I said, we have a dedicated lecture on the reinforcement learning. Reinforcement learning, you see, it's basically based on the concept of award and penalty. Okay, so it's a machine learning framework where decision making agents learns to solve problem through trial and error interacting with the environment. Alright. So unlike supervised learning, which relies on the teacher, that is, we have the input output data provided. Okay, reinforcement learning is learning with a critic basically. Okay, that provides rewards or penalties, okay, after a sequence of action is taken. The core elements in the reinforcement learning are agent, okay, who is the learner or the decision maker, then environment, okay, everything outside the agent interacts with, then the state is a representation of the current situation, okay, and the action, okay, set of possible moves available with the agent in a given state, and the agent's goal is to maximize the cumulative reward over time. Okay, so this concept is explained over here. Robot observes the state, then it takes action, okay, and based on the action, environment gives the reward, okay, and then robot updates its brain basically, and the cycle is repeated. The key challenges here are, that is the credit assignment basically. Okay, agent must learn balance between exploration and exploitation. Okay, exploration means it should explore the various possible options, and exploitation means that working with the same reward again and again, repeating with the same reward. Okay, so that is there. The major algorithm of the reinforcement learning are Q learning, SARSA, and the model based learning. The applications are the autonomous navigation, okay, and avoiding of the obstacles. Okay, so these are there. So to summarize, you see, it is essential in robotics wherever sensor data is too complex for handcrafted rule. Okay, there we definitely want to go for the machine learning. Okay, whether it's a picking of an object by a manipulator or the motion of a mobile robot. Okay, so the three paradigm we have seen: supervised, unsupervised, and reinforcement learning. Okay, and we can apply them based on what type of data we are available. Okay, and many people spend a lot of time building complex machine learning solution, and only to find out that they don't solve the right problem. So whenever we are trying to build a machine learning solution, we should always keep a problem in our mind. Okay, so that will help us in creating correct machine learning solution for the. Okay, so these are the references. In the previous lecture, forgot to include the reference. So this is the reference which you can refer: Introduction to Machine Learning with Python. Okay, and there is another good textbook on the machine learning, and some resources from skitlearn. Thank you.